Hello everybody, I'm Alice Brunello, a Cututela student from Italy. The title of my presentation is Green in Space Transportation with Tether Technology and regards the use of space tethers for moving in space. Luckily, I'm not able to be there, but I will come to Madrid in September. I hope to see you there soon, but in the meantime, I hope you enjoy my presentation. In this presentation, first I will talk about electrodynamic tethers, with an explanation of how they work. Secondly, I will describe an electrodynamic tether system used for space debris mitigation, talking about the ETIPAC initiative that proposed to find a solution to the orbit satellite using space tethers. Then I will talk about electrodynamic tether systems used both as a reboost and station-keeping device. The last part of the presentation will have a focus on publications, conferences done and foreseen, and on the future developments of my PhD thesis. Electrodynamic tethers, physical principle. An electrodynamic tether is a long conductor that is able to interact with the ambient plasma of LEO orbits. Using a plasma contactor, a current starts circulating on the tether and, thanks to the Faraday's law, a Lorentz force appears. Depending on the current verse, the Lorentz force can be a drag or a thrust on the satellite, and in particular, to generate a thrust force, a power supply must be fixed on board the satellite to reverse the natural current flow. Electrodynamic tethers for space debris mitigation, the ETIPAC initiative. In the last several years, the need for an alternative to chemical propulsive system for LEO Earth orbit satellite has become increasingly evident. In fact, the 5-year recommendation for satellites disposal is currently leading the space community to install disposal on-board satellite to be mounted prior to launch, an alternative to chemical propulsive system for the orbiting satellite when they will be at the end of their operative life. Among all the technologies, electrodynamic tethers seems a promising option because they can provide adequate drag without the complication of the combustion and with a minimum impact on the space environment. In the context of space debris mitigation using tethers, both the University of Padua and UC3M are working with an international team on the ETIPAC initiative. The ETIPAC initiative wants to demonstrate the capability of the tether technology to the orbit satellite using tethers in low time, thus respecting the 5-year recommendation for satellite disposal. The project, that involves universities and industries from all over Europe, is divided into two fundamental parts. ETIPAC, concluded in late 2022, had designed and manufactured a deorbit device prototype and had reached TRL 4 after 3 years of development. ETIPAC F, still in progress, that proposed to reach TRL 8 in 2025. The ETIPAC deorbit device is composed by two modules, the electron emitter module and the deployer mechanism module. The deorbit device will fly in 2025 with an in-orbit demonstration mission, in which it will be launched into a 600 km circular orbit with 51 degrees of inclination. After the initial phase of satellite stabilization, the two modules will be separated, even if they remain connected by the tether. The tether will be 500 meters long, will have a tape shape, and will be made with two different materials, aluminum and PIC. The electron emitter module hosts the active device called the electron emitter that exploits the emission of electrons in the Earth plasma environment in order to establish the flowing of the electric current through the tether. The deployer mechanism module contains the spool and the deployer mechanism that is able to extract the tape from the inside. Both modules are completely autonomous and use a very low power to operate. In this slide, I present the current design status of the deployer mechanism module through a video of the verification test that I personally conducted in late 2022. The deployment tests were used to check the ability of the deployer mechanism to deploy smoothly different sections of tape. And in particular, the initial and critical separation phase in which the two modules start separating was simulated. As you can see in the video, the deployment is smooth and stable, and no stop-and-go behavior occurred during the deployment maneuver, and no tearing of the tape appeared. So, we are really confident that our system will work properly once in orbit. Electrodynamic tethers for reboost and station keeping. As already told you in the introduction, an electrodynamic tether can be used also to provide a satellite thrust, in example to perform a station keeping maneuver. The current that must circulate on the tape depends on ambient values like the plasma density and the magnetic field, the design parameters that, once they are selected, they cannot be changed during the missions, and the cathodic contact that depends on the type of the electrodynamic tether chosen. Thus, according to the formula, the only control parameter must be the electrical power, and we can vary the electrical power to fulfill a certain objective. So, the goal of my studies was to contribute to find convenient control laws for the electrical power, and in particular, three control strategies were identified: constant current for reboost, constant power for reboost, and high drag compensation for station keeping. Also, for each strategy, the long-term evolution of the orbital element was investigated. The high drag compensation strategy aims to neutralize the resulting power. The average current to perform a station keeping was calculated, and, with the use of the simplified assumption of the Earth magnetic field modeled as a centered dipole, analytical results and simulations using BETSMA software were performed. The radius is keeping constant according to our hypothesis of station keeping. The eccentricity is almost zero, while the inclination decreases almost linearly over time. The long-term evolution of the orbital parameters were performed also for the first two techniques, thus the constant power and constant current, that allow to perform a reboost maneuver. For these strategies, high inclination orbits were simulated. High inclination orbits have regions where the electrodynamic tether cannot operate, due to the reverse of the sign of the motional electric field. To operate as a reboost device, an electrodynamic tether must have that the product between the motional electric field and the current flow is negative. But for high-inclination orbits, there are regions where the product becomes positive because of the motional electric field change sign. To overcome this issue, a capacity factor was included in our simulations. The capacity factor is defined as the fraction between the time with Lorentz force on and the total time of system operation. In both cases, and according to the robust assumption, the radius increases, while both the centricity and the inclination vary over time. In each simulation on the left, you can also see intervals of time in which either the power or the current goes zero. These intervals correspond to the regions where the motional electric field has the same direction of the current flow and the system cannot operate. Publications and conferences. In this second year, I attended two conferences. The first one in Paris in last October, in which I presented the article Deployment Functional Test of an Electrodynamic Tape for Space Debris Mitigation, and for which I was elected as finalist of the Luigi Napolitano Award. The second one in Singapore last April, in which I presented the article Space Debris Mitigation using ETIPAC, a compact electrodynamic tether system for deorbiting. Next October, I'm going to Baku to participate to the International Astronautical Congress with the article Optimal Design and Current Control Strategies of an Electrodynamic Tape for ISS Station Keeping, that is still under development. In this slide, you can see a list of all the publications I did during the PhD course. Future developments. In the next few months, I will work hard on the paper to be submitted to the International Astronautical Congress in Baku. Specifically, I will work on optimization code to find the optimum tether length for the ISS station keeping, and then I will perform simulation using BETSMA software for ISS station keeping with two strategies: instantaneous hydra compensation and zigzag strategy. And then in September, I will submit the final paper for the Congress. In parallel, I will help the UniPD team on the test campaign on the engineering qualification model of the ETIPAC initiative. In particular, I will help in the qualification test of the deployer mechanism module with 500 meters of tape length. Thank you for the attention. I hope you enjoyed my presentation. If you have any questions, please send me an email. I will answer you as soon as possible. Bye-bye.